he said, but there are miles and miles of beach and hundreds and thousands of starfish. What difference can you make? And she bends down, picks another starfish, throw it to the ocean, and she says, I made a difference for this starfish.
Beautiful. Yeah.
And the man listened to her and says, okay, I will walk with you. And they walk together, throwing starfish into the ocean. So I don't have a magical knob to make a huge cultural change in society, to change the culture. Let's say I'll be happy with the change the culture in computing, but I'm trying to do one starfish at a time. And every time I have one of my PhD students says, I don't want to go to industry. After what I've been hearing from you, I do not just want to go to Silicon Valley. So it's one starfish.
Welcome, Moshe, to the Journeys of Scholars.
It's good to be with you, Adel.
Thank you, Moshe, for being with us. So, Moshe, as you know, academia is a perfect place to sharpen our research abilities towards excellence. In general, it might be less helpful, however, in terms of thinking about life in general and mentoring where this research is sort of happening here. So this, conversation is going to be about your research, but also how you think about these overarching, parameters that condition research in general. So, Moshe, you are the university professor in computational engineering at Rice University, where you lead also the Technology, Culture, and Society Initiative. Your research focus is on application of logic to computer science, including databases and finite model theory. You are also engaged in these multi-agent systems of how knowledge sort of propagates, and computer-aided verification and reasoning in general. And recently, you've been a quite outspoken scholar about the impact of information technology on society in general. You have authored and co-authored many articles, counting about 700 plus, and 2 books, one about reasoning about knowledge, 2003, and finite model theory and application, 2007, with co-authors. You are also the senior editor of communications of the ACM, after serving some time as an editor-in-chief for several decades. You're the recipient of numerous awards and scientific fellowships, among them the Blaise Pascal Medal, the IEEE Computer Science Godey Award, and some other. The list is very long. I mean, I can go for a very long time to list all of these things.
Please don't. Please don't.
You're also the fellow, one of the fellows of many societies, including the National Academy of Sciences. And recently, you've been awarded an honorary doctorate at University of Gothenburg, one of 8, I believe. Now, Moshe, one of the things that hit me when I was browsing around and reading about your portfolio of research is actually on your website. When one can read that your motto is "Theorems are forever, the proof, the whole proof, and nothing but the proof. Dare to know," and that's in Latin. Tell us a little bit about that background for that motto, please.
When I was about, I think 10 years old, one of my math teachers decided to have a math club, after hours club in mathematics for kids who showed more talent in mathematics. It didn't last very long. The whole enterprise, I don't know, but it wasn't very long. A few meetings, somehow it fell apart. I don't remember exactly even why. But my mother told me later, I don't have direct memory of this. My mother told me later that after the first afternoon meeting, where I remember he talked about matrices, okay? That's what I do remember. He talked about matrices, and I think he even talked about determinants. And I come home, and my mother asked, how was it? And she said that I said it was beautiful. And my mother had no background in mathematics, okay, other than doing very basic arithmetics. And so she didn't. She was a bit puzzled, and she said, "You mean interesting?" And my reply was, "No, I said beautiful. It was beautiful." So there is beauty in mathematics, and it's very hard to explain beauty. I always puzzle. For example, many people find mountains beautiful,
Right.
and I was always puzzled by that. I understand why we find people of some sex. There is I understand the evolutionary basis for finding the beautiful. Okay, just sexual attraction. If we don't have no sexual attraction, no reproduction.
Right.
So nature programmed us to be attracted to find people of some sex attractive. But mountains, and in fact, if you go back, people used to think mountains is a dangerous place. Outlaws went to the mountains. But
Yeah.
today we find mountains beautiful. I'm puzzled. I don't know why. I find them beautiful. So I find mathematics beautiful.
Hmm. Hmm.
And to me, one of the most, we talked about kind of cultural milestone, the biggest milestone in kind of cultural history, right? The human being develop speech, and then we develop writing, and then we develop the print, and now people talk about the internet as another phase of this.
Right.
But I think the Greek invention of mathematics is equally pivotal. They're not the first one. I mean, other people did, other countries did mathematics. Chinese, Indians, Babylonians. I mean, we find Babylonian tablets with Pythagorean triples.
Hmm.
But the theorem and the proof of the theorem, that was an amazing thing, because it's an argument that is just, people call it the high road to truth.
Right.
It's an argument that is so airtight. After that, you said, okay, the debate is over.
Hmm. Right. Yeah.
And in fact, the legend is that when the Greeks, when Pythagoras found this proof, for him it was a gift from the god, and he slaughtered an ox to thank Apollo for this wonderful gift.
Right.
So to me, the fact that you can prove a theorem and it's an airtight argument,
Hmm.
it's just an amazing thing. There is just amazing beauty in it. So
Right.
that's what I like about it. Once you prove a theorem, it's there. It cannot be unproven. I mean, of course, as you know, proof can get it's a bit simplistic, because proof can get very complicated.
Sure.
How do you make sure the proof is correct? People found bugs in proof. We go to the foundation of set theory and what axiom are you use. I mean, there are, but when you first come across proof, you say, wow, this is absolutely amazing.
Hmm. Yeah. Yeah.
So to me, this is what I said. I think that this is an amazing thing. However, in my own research, I have come to get a bit more nuanced view, because in particular in the area of algorithms, there are many things we cannot prove.
Right. I was going to actually ask you here. So yeah, let's hear.
Okay. For example, the amazing success of deep neural networks. We do not fully understand it. It's an empirical fact. It's an amazing success. A Boolean satisfiability solver have made amazing success over the past 25 years. We now solve routinely industrial problem with millions of variables. Why? We don't have a theory to explain it. It's considered a major open problem in complexity theory. Explain. It's an NP-complete problem. It's supposed to be hard. We used to think NP-complete means hard.
Yeah.
Now, we're solving huge instances. What's going on here?
Yeah.
So now I'm coming to look at as something a little more akin to what happened in natural sciences, where you can have theories, but also have experiment. And if you look at the natural sciences, especially the physical sciences in particular, we see it as the two legs of the physical sciences, theory and experiment. There's some debate. Some people want to add data science and simulation as other legs. I'm one of the traditionalists. I think that two legs, theory and experiment, except that our understanding what is a theory evolves. We used to think of a theory, something you can put on one page.
Yeah.
Okay. Now you have climate models, which are, who knows, hundreds of thousands of lines of code. Okay?
Exactly. Yeah.
There are still theories, okay, but it's not exactly like Maxwell equations. Okay. So our notion of theory has evolved. Our notion of experiment has evolved. Much of what we do today, for example, in astronomy, is first go take pictures, so to speak.
Yeah.
Then you analyze the pictures later to see what you see. It's not as if I have an hypothesis and I'm going to experiment on it. You reverse the order. So the way the two legs interact become more sophisticated and less simplistic. But I still think of it as two legs. And in computer science, we kind of have theory and experiment, but we don't have necessarily a nice ongoing feedback loop between them.
Right.
I mean, what should happen is that good theory should predict experimental findings, and some experimental findings should say, we don't understand this. We need a theory to do that.
Right. A revision of the original theory and evolution.
Yeah, we need to understand. Deep neural networks are very effective. Is there a theory to explain it? The same way that I remember years ago when I was at IBM, people discovered what they call high temperature superconductivity. And that inspired lots of follow-up research. Can we explain it? This was before that people thought that superconductivity happens very close to the absolute zero.
Right.
And suddenly we find it, instead of doing it with liquid helium, we do it liquid hydrogen,
right.
liquid nitrogen, which is much, much, much warmer. Still cold, but much, much, much. You can go to a chemical supply store and buy liquid nitrogen. Right. You can buy liquid helium, but it's much more expensive. So there is an ongoing feedback between theory and experiment, and ultimately, if there is a theory that we don't succeed in verifying it, we question: is it a scientific theory? In fact, we say if it's not falsifiable, then it's not a scientific theory. This is the Popper principle. So I think in computer science we are slowly crawling towards something more similar.
So what would the revision to your motto be here, Moshe? Given the maturity of your insights,
theorems are forever, but their applicability to real life is in question.
Yeah, please.
Okay, even take Pythagoras theorem. Okay, it's true in the plane. Well, where do we have planes? We don't have real planes in life. We are on a spherical planet.
Exactly. Yeah.
So we don't exactly have things. It's a good now we say, okay, unless you're doing things on a planetary scale, if you just want to divide, if we have two Egyptian brothers are trying to divide the field inherited from the brothers, plane is a good enough approximation. Okay.
Right.
But we now understand that yes, in what they call in Platonic space, it's there, but applicability to real life is a different story.
Yeah. Yeah.
And in fact, I read a book a few years ago that really influenced my thinking. It was a book called The Fables of Economics. And it was written by a distinguished Israeli economist, Ariel Rubinstein. And he said that much of economics is done on theoretical models. It's like computer science. We have a theoretical model. But the applicability to real life is not always airtight.
Yeah.
And so today, that's why managing the economy is a difficult problem, because there's the gap between the complexity and the messiness of real life and the cleanliness of the mathematical model, where you can have theorems, but it's not clear what the theorems say about real life.
Right, and this is my background in social sciences, for example. It's a huge messiness in terms of how to even formulate a theory. It's in its worst case, you might have equal number of theories given like the researchers in the field. Like there's just a flora of theories because it's so hard to experiment in these open systems. I mean, one of the things that and even astronomy that's maybe the reverse problem. There's just one iteration of the solar system. There's just one realization of the galaxy. So you have hard to experiment on type of systems.
This is one of the mysteries, is that we don't really have a theory that says why this universe is the way it is. I mean, at the end of the day, this says, well, they've tried to offer a kind of general theory to explain it. I mean, again, this is way out of my field, but string theory is somehow a meta explanation. But there are other solutions. And so if you're saying, well, there must be other universe, this is how metaverse comes into play, right? You say, well, if this is just one arbitrary solution, how was it selected? And unless you want to go and say God selected this particular solution, then you said why there are no other solution. That's why the people said there must be multiverse.
Right.
But this is multiverse is an example of a beautiful scientific theory that is not even clear that it's falsifiable. So there are physicists that say it's not a theory. It's a story, but it's not a theory.
Right. And in a way, those theoretical developments in terms of imagination or imagining alternative explanations are conditioned by the society and the technology we live in, the instruments that we can mobilize. I mean, in the time of Galileo, there were barely any, instruments or telescopes. And then that was just a myth, but then it became the scientific truth. And there's this coupling between technology or instrumentation, I would say. And who knows,
Yeah,
in the future, we
yeah.
might be developing a
We
technology.
might, we might, we might. But the dark side of the theorems are forever is the people call it lost in math.
Yeah.
And certain economics and physics and even some computer science now are subject to criticism. You fell so much in love of your math
Yeah.
that you say, well, between my math and the real world, I like my math better because of the cold elegance of mathematics. People
Exactly.
says, in fact, I heard once a very distinguished physicist, um, Nobel Prize winners, gave a talk on the multiverse theory.
Hmm.
And I raised my hand at the end and I said, it's a beautiful theory, but is it falsifiable? Because if it's not falsifiable, then the Popperian principle,
Hmm.
it's not a scientific theory.
Hmm.
His answer was pretty much says, I'd rather give up the Popperian principle than this beautiful theory.
I see. I see.
Okay.
It's a commitment to the theory more than the actual science in that way.
The theory is so beautiful, I'm not willing to give it up.
Right. Right. So this actually leads me to a really important question in terms of what's going on in the AI development. I mean, you mentioned, the theorems in terms of, applying, say, logic to computer science. So this is sort of the deductive approach to computer science and AI development, which was dominant in the early phases of the 50s and onwards. And now we're seeing, this rise of deep learning, which is sort of beyond the rise. I mean, the whole large language models with ChatGPT and generative models in general are the flip side of this. So basically, these inductive approaches, we have mathematical operations that those we understand are well specified, but what they actually do is still, to a large extent, hard to unbox, right? And so we have these two approaches, which is one is these deductive and the other one is the inductive. And I know that you've been working on the synergy between them, the neuro-symbolic AI. So tell us a little bit more about this sort of interaction between the two fields, because this really relates back to the theorems are not forever. Like, we understand what deep learning is, but it's very hard to unpack. And so please unpack this for us.
So I got into this graph neural network, GNNs, because I've heard the talk about it, and I was deeply skeptical. So I had a Brazilian colleague, Luis Lam, who has done important work. He was one of the pioneers of neuro-symbolic reasoning. And I said, I just don't believe that this approach will work well on optimization problems.
Hmm.
So let's try to run some experiments, and then write a paper saying, no, it doesn't work. Except that it did work.
How?
When we ran the experiment, and it turned out that it actually worked fairly well. We looked at TSP and tried to do some approximation for TSP, and again, we don't have any good explanation, but it actually worked fairly well.
TSP, just to explain for that.
A traveling salesman problem.
Mm-hmm. Oh,
Okay.
The
which is a kind of a graph theoretic problem, so you can perfect for GNNs, and it really worked. It worked much better than we expected, and we published a paper on this, and the paper now getting lots of citation because I said, look, it actually works. And I said to say, my intent was to publish a paper debunking GNNs. That was the intent. But the reality stared at me in the face and says, I said, it's NP-conp problem. And if you look at the GNNs, they are essentially polynomial time algorithms.
So let's unpack this for those that are introductory to the graph neural networks. That's what the GNNs are. So basically, they are neural networks, but they have a graphical structure. Which
instead of looking at maybe a text, which is just a string, or at images, which are just two-dimensional, arrays.
Yeah.
They take a look at the graph structures, and they basically you the same way that the neural net over a string or an array kind of iterates a computation of weights until it gets to the output. Here you kind of iterate again some computation of weights, but each node only look at its neighborhood. So you are using the graph structure. Okay, I'm grossly simplifying, but essentially.
And the graph represents here knowledge flow or sort of flow.
No, the graph, in this case, we're looking at traveling salesman problem. The problem is given to us as a graph with weights on the edges. Okay, the problem is given to us as a graph. So now you basically say, instead of trying to encode this graph as some kind of a string, there are ways to encode graphs as strings, but then you lose the locality.
I see.
And the observation here that when we think about graph, it's important who are your nodes, sociology.
Yeah.
It's important who are the people who is your family, who are your friends, who was your, things like that. So we want to take advantage of the graph structure. So GNNs were neural nets adapted to graph structure to take advantage of locality.
I see.
But we are looking at the question which we know is computing finding the least cost tour of a graph. And we know this is an NP-hard problem. And it turned out that these GNNs were computing pretty good approximations for it. Again, we can prove nothing. So there's no theorem here. Okay.
Right.
I'd love to have a theorem. Okay. Yeah. But empirically, so we are in the stage, if you think about very often how science is done, sometimes you have a theory and then you go and you try, you have a theory. Dirac has a beautiful quantum. He was able to quantize Maxwell equations, and out of this there must be a particle of negative charge, okay, or positive charge. I'm sorry, must be a counterpart to the electron, and then eventually people found the positrons. Okay, so the theory predicted the experiment. Many other cases, we do experiment, you find some phenomenon, and then you try to explain the phenomenon. In this case, at this point, we don't have an explanation. We have a phenomenon. And it's just part of my interest now in trying, can we explain this phenomenon? What is going on here?
Right.
What is the algorithmic power? Now because I'm now solving algorithmic problems. It's not, the problem with classification is, okay, what you say is that I'm classifying images. Okay. It's just harder to define, the ground truth is what humans say, and we're trying to approximate the ground truth.
Yeah.
But here the ground truth is a mathematical fact. Okay. What is the minimum cost tour on this network for the traveling salesperson? Okay. So we have very cold, hard ground truth. It's not just classification comparing to humans. There's no humans in the picture.
I see.
We're not trying to imitate humans. Okay. We're not trying to generate text that people consider, oh, this text looks so good, it must have been generated by a person. We're not trying to do the Turing test or anything like that.
No.
We're trying to solve classical optimization problems. Start out of a course, probably at Rice, is we teach them in the second semester. We start to talk to them about solving algorithmic problems.
Yeah. So then just to dig deeper into, so the graphical neural networks, they work in this particular problem. Then you have this algorithm. It works, but it's unclear why it's working.
It's unclear why it's working.
Yeah, and this is where the symbolic computing comes in, I guess, like the logical side of trying to devise some kind of a algorithm. I'm assuming now, like algorithm on top of it to unpack what's going on in the GNN, or
well, the neuro-symbolic is a rather vague term, and it means different things to different people. Okay, there are different interpretations of this. I mean, the point is that we have. I look at it even in a bigger way. Okay, we have I consider to have three big waves in AI. The first big wave going to beginning was what we call symbolic reasoning. So if you go to the pioneers, John McCarthy, you go starting in even the early 50s, and they thought, what is intelligence? Intelligence is logical thinking is intelligence. So they were trying to that's how they're trying to pursue it. And the kind of the ultimate success was the rule-based systems, kind of what we call expert systems. And in fact, there was even the famous Japanese fifth generation project, okay? We'll build specialized hardware just to be able to do this kind of rule-based reasoning.
Right.
And ultimately, the approach has its accomplishment that people now forgot, but just based on rule-based, we're able to do fairly good medical diagnosis. This basically going back better than doctors. People have tested it, and because you can encode lots of knowledge more than a single doctor carry in its head. So basically, it was knowledge of other doctors, but you interview experts, you formalize everything, and you got a very good diagnostic system. But the approach kind of petered out. And then the other approach that pushed promoted in particular by Judea Perel, and he says, no, when we think about the world, we also think about probabilities. How likely is something to happen? It's not just yes or no. Yes or no is too simplistic. We need quantitative, and quantitative has to do with also with probabilities. With certain things, I always sometimes when I see TV, and a lawyer asks a witness, but isn't it possible that something happened? And I always says, I want to be that witness. Because if the lawyer would ask me, isn't it possible? I would say, please define possible. Okay. I said, it is possible that you are a humanoid lizard. Okay. It is possible that I'm imagining that I'm a witness. That all kind of things are possible. I said, define possible. So Perel says, well, we can just say possible is fairly meaningless word. Let's talk about probable. What is the likelihood that something will happen?
Yeah.
And in fact, people have even worked on trying to integrate the symbolic reasoning with probabilistic reasoning. Okay, all the way from logics of likelihood and compiling logical probabilistic inference problems to Boolean reasoning problems.
Yeah.
And so people have said, okay, with these two powerful approaches, let's see how we can integrate between them.
Basically, the first one is deterministic.
Symbolic. The second one is probabilistic.
Yeah.
Okay. And then I think the third wave, and again, I'm simplifying, but the third wave to me is the wave of deep learning, of neural nets. And people forget that neural nets started as logic. Okay, the initial idea was we want to try to understand, going back to the 1940s, we want to understand how people think. And so we need to take our logical circuit, so to speak, instead of just having and ors, we need richer notion of circuits.
Yeah.
Going beyond and or, we need to have what we call generally threshold circuits, because people have already done the experiment and so how neuron essentially work. Okay, they get incoming signals, and the signals are somehow weighted, and then the neuron fires based on some weighting scheme. Okay, and so neural nets were proposed in the early 40s. Okay, about actually, I think I have to go find the paper. I think we are now approaching this year is the 80th anniversary of that paper. I have to find the precise date now, by Pitts and McCullough. Okay, so, and then there were very early on in AI, people says, well, why don't we try to use this idea for doing machine learning, and all kind of attempts to do it, and many of these attempts failed, and they end up resulting in the so-called AI winters, because people made grandiose promises. There was huge optimism, and then they couldn't quite deliver.
Right. Funding dried out. And
in fact, funding dried out, research dried out. In fact, I heard a story from from a colleague who told me about the conference today called Neuro-Ips. It used to be called NIPS. In 2000, he was there. He said there was a reception, and he remembered Hinton, Jeff Hinton. Now we're getting, of course, huge attention because he just decided to quit quit Google.
I was just reading that the other day. Yeah.
Yeah, this is all over the news now. Jeff
Mhm.
Hinton is quitting. The father of AI is quitting Google because he realized that AI can be dangerous.
Mm.
But he remembered 23 years ago, I think it was 2000, that Jeff Hinton is standing in the reception, and he's standing alone in a corner nursing his own drink. No one talks to him because he's the crazy guy that still believes in neural nets, while everybody else has given up on neural nets.
Right.
And in fact, if you read the Turing Award citation for Bengio, Hinton, and LeCun, the citation mentioned their persistence in pursuing the idea of neural nets, while the community at large say no, they don't work. They've given up on it, and they just kept hammering in it and hammering in it.
Right.
In general, again, the rest of the community was against them. They were for a while all alone, and only in about 10 plus years ago, things kind of turned around.
Mm.
And suddenly they were, first of all, they were very good at image recognition. And since then, now you go to the, to the grocery store.
Yeah.
If you say anything, I'm a computer scientist. Oh, tell us about ChatGPT. Tell us about ChatGPT.
And the
Okay.
key moments here, I mean, there's a footnote here. We'll continue about this neural symbol AI. So why did it turn like around? What do you think? Was it just a vast amount of data that was suddenly accessible?
So I think there were three things came about. One is that people have continued to work on the algorithms, making it better and better algorithms. The quality of the algorithms have improved. The hardware is getting more and more powerful. GPUs became widely available. GPUs have been critical. We always thought of GPUs that are good for gamers, and it turned out that they are really the key tool for machine learning today, for deep learning, are GPUs. So the availability of GPUs was a huge enabler. And, suddenly we had big data, which we didn't have before. Before that, if you want to do supervised learning. So if you have images, somebody had to tag the images. So it used to be that you ask your graduate student to tag the images. Okay, so maybe they'll give you thousands of images. How many images can you ask your students to tag? Okay.
Exactly.
Then Mechanical Turk came around, and you could pay people pennies per image, and they would tag images. So you could go from thousands of images to tens of thousands of images.
Then you have ImageNet and other types of data coming.
But then internet came around, social media came around, and now you can just harvest images from Instagram and from all these other places. You have all these images, and they are tagged because people write, I'm taking my dog for a walk. My cat is staring at me. So it's not intentional tagging. It's usually kind of just people describe something, but it's actually turned out to be good enough.
Yeah, right.
And so this combination of better algorithms, which people have been working for decades on, better algorithms, much better much more powerful hardware, and suddenly big data. And turned out that it took us a while to realize that, as opposed to human learning, which can happen with what we call, small data sets. Human beings are also very good. I can show you a few pictures of some animal you have never seen before. A raccoon. What is it? That's a raccoon dog. This is one of the theories that how COVID came about, from raccoon dogs. And I said, wow, I have no idea. I know what is dog. I've never seen a raccoon dog. You show me a few pictures and I can recognize raccoon dogs after that. Okay.
Right.
Doesn't take much. You show me 5 pictures and I'll recognize raccoon dogs. But it turns out that for deep learning to learn it requires huge number of images. But suddenly in the early 2010s, everything came about just right. Everything converged, and poof, suddenly we have a success rate on this repository of images that is even better than human performance.
Right.
And it was a turning point. And then people start putting more investment, more research. GPUs were getting even cheaper. People applied to text, and generative AI came about. There was just a blossoming of research, amazing blossoming of research right now.
Yeah.
You look at these conferences, they have amazing number of submission. I mean, the problem is right now, it's just impossible to follow what's happening in the field because it suddenly exploded. Okay.
It's exploding, exactly. And there is, all this pushback that we'll be coming back to, which is the impact of all of these technology on society. But one thing that I before we go into that topic, which is, what's now the game plan for, say, the symbolic AI community, if there is any. Like, if there was the deep learning community on the slowdown, now it seems like there's almost a reverse relationship. And also, relating to the conversation with Judea Pearl about causal inference, that what's the role of causality? That's largely, I would say, has a component of symbolic AI thinking in it, obviously, but from the causal inferential perspective.
So one way to kind of even generalize symbolic AI. So one is to say there have been in symbolic reasoning over the past 25 years, there also have been dramatic progress. It just never got the attention because it's a bit more esoteric. You cannot immediately show success applied to logical reasoning. And also the community has done, in my opinion, a huge marketing error. The new SAT solvers are called CDCL solvers. And CDCL's close for conflict-driven closed learning. And it is as obscure as the names of the variants of the viruses, okay?
Yeah.
XB5.11, who can remember this kind of stuff? And I tell my colleagues, imagine you call it deep solvers instead of CDCL solver, deep solvers.
Suddenly is like a big thing, yeah.
It's a big thing. In fact, if you want you go even farther, call it profound solvers, sounds even better. Okay?
The community needs a PR division.
So taking learning and calling it deep learning it was really because the network was getting deeper. I don't think people intended it just as marketing, but it was unintended. It was a great marketing move because deep is a good word. Unless you're drowning in a pool, generally there are some words that are good words. Green is good, open is good, inexpensive is good. All kind of things that are good. Deep sounds good. Okay. Again, unless you're talking about the deep side of the pool and somebody drowned in it. But generally, deep is good.
Sure.
So deep learning sounds like, wow, this must be a powerful technique, right? Because it's deep. You tell them, no, it just means many layers in the network. But anyway, it was both a technical success and again, the fact that you could not handle deep network because you had the algorithms and the hardware to do it. And you need many more parameters, but you have big data that enables you to train them. So all of this came together. Now, in the same time, in symbolic reasoning over the past 25 years, again, dramatic difference between solving problems. There we talk about the dimensionality of the problem. How many independent variables do you have? And we went by the early 90s, we could solve problems with hundreds of variables. And now we solve problems with millions of variables.
Yeah.
Very dramatic success. So now I think the challenge for us is to figure out, okay, we have the three waves. And I don't think it's to be either or. I think, okay, each one has its role. How do we integrate them? To me, the real challenge now
integration
is how do we integrate these things? And my work is more integrating. Really, my work is integrating the symbolic and the probabilistic. But something that does come out of it is that the problem with classical logic, it lacks nuance. It's just true and false. Okay. And certain things are simple, true and false. Okay. Am I talking to you right now? Yeah, I'm talking to you right now. It's a fact. I don't believe in the brain in a vat theory. Okay, right. I'm talking to you right now on Zoom. Okay, so this is absolutely true. But But I tell when I talk to students I teach a logic class. I tell them, okay, there are certain things are beyond dispute. I'm standing in front of you. But take the statement, Vardi is a great teacher. Well, I said now there are going to be different opinions, and people will not say true or false. You say, well, he's pretty good, or he's very clear, but he gives too much homework. There'll be more nuance.
Yeah.
And so, how do we take logic and make it more nuanced by making it more quantitative? So the simplest way to look at it is if you have a logical formula with atomic propositions, there are 2 to the n possible truth assignments. So classical logic looked at 2, I would say, extreme conditions. Okay, and the 2 extreme condition was: is it always true? That is to say, there are 2 to the n. There are all assignments are solutions. So there are 2 to the n solutions. And the other extreme was there are no solutions, 0 solutions. Well, that's just, you look at the 2 extremal point.
Yeah, exactly.
How about, for example, would be interesting to know that the majority of assignments are solutions.
Yeah.
So you say this formula is more likely than not. Lawyers would say, this formula is more likely than not to be true.
Right.
Well, now we need a different way of reasoning. We can't just reason about, does it have solution or does it have counterexamples? Now we're asking, how many solutions does it have?
Right. So
and so now we're doing, I would say, quantitative Boolean reasoning. So much of my research today is quantitative Boolean reasoning, and that bridges us both with probabilistic reasoning, but it turns out that it's a bridge to reasoning about neural nets. If you want to understand, somebody give you a neural nets and you want to understand, analyze it, very often you need to reason. You want to understand, well, it can have many inputs. Can I say something will be true with high probability across all inputs?
Right.
Then you need to again bring back this quantitative reasoning, and this is the direction that already one of my students went on to explore. He's now Kuldeep Mill, who is now a professor at NUS, assistant professor at NUS, and he has when he went on to explore applications of quantitative Boolean reasoning to the analysis of neural nets.
Basically, taking the neural nets as the subject of study, but applying logic
symbolic, yeah.
Symbolic,
But this is just one of the many approaches.
Yeah.
Some people are saying, some people are trying to, some people look at, if you think of logic, one of the things very often is logic. Some people say, well, it's not so much about logic, it's about reasoning about models. Do we need to have models? So so basically, if you look at just classical neural nets, there's no model. You just you get raw data. Okay. And I said, if you think of language, it's just a string. Okay. If you think of an image, it's just an array of pixels. But Amnon Shashua, who is he was a professor at Hebrew University who did machine vision, and he co-founded a company called Mobileye, which Intel bought for billions of dollars.
Oh wow.
And about 5-6 years ago, he wrote an article about autonomous driving. And first he asked a sociological question: how much safer should AV be compared to human-driven automobiles? He said, utilitarian would say, if it's a little better, we should do that. Let's suppose that you prove that it's 10 times safer. There's already a reason to use this technology.
Right.
He said, I don't think it will fly. Why? He takes United States, where somewhere like, maybe 40,000 people die every year from car crashes. Suppose we reduce it to 4,000. Okay. It still means that every week, about 80 people will die from car crashes caused by AVs.
Exactly.
He said society will not accept it. Society is very forgiving about human error. To err is human. But they are not so forgiving forgiving towards machine errors. Even a philosopher would say, but we have saved 90% of lives.
Yeah, it's sort of being racist against machines, if you like.
So he said we have to reduce it to something that society will accept. And he said it has to be, in his opinion, you know, 1,000 times safer or 100 times safer. You know, it has to be much, much, much safer. Okay, by a huge factor, not 10 times safer. He said this is not enough. He said if every week there is a couple of accidents caused by AVs, maybe people will accept it, but not tens of accidents.
And the reason is most likely because explainability, right? We can understand why a human causes a.
We are human. We are forgiving ourselves. We know that how easy it is to make mistakes. Okay, machines. We have no empathy with machines. Okay,
I see.
We have no empathy with machines. We are not. Look, we are not forgiving towards, for example, people who drink and drive. Okay, then we are not forgiving. We say you could have been avoidable. But if you drive and your baby is in a car seat, on a back seat, and your baby starts crying and distracts you, we says, well, for the sake, this could have been us. Okay, so we are forgiving towards many kind of things.
Yeah, I see.
So the issue. So he said, okay, how are we going to? So he said, suppose we will do what some companies have said to do. We'll just do what's called end-to-end training. We will just take human-driven cars, and we will take the data and use deep learning to learn from human, all the sensors, everything, the cameras, the LiDAR, everything, and we are going to learn from that how to drive a car. And he calculates if we want to use this to get right now, if we want to try to make a car 1,000 times safer, right now in the United States, really the real measure is not how many people get killed per year, but how many fatalities do we have per billion VMT. VMT is vehicles mile traveled.
Oh, I see. Yeah.
And so because the population is larger, there are more people, there are more cars, how do you know whether it's safer? You look, okay, for each billion VMT, how many people will die? And we have done an amazing job in making cars safer. And now the answer is, now it's under, I think United States is under 10 people will die for billion VMT.
Wow, that's a huge improvement.
Okay. So if we want to make it safer by a factor of 1,000, he calculates that we'll have to test and train, to train and drive train billions of miles. He said it's just not realistic. So he said if instead of just doing machine learning, you combine machine learning with a model of what's happening when you drive and how accidents happen, then you can be much more effective.
I see. This is bringing symbolic part into like the.
So to me, once you're talking about models, you're doing symbolic. I take symbolic, not just, it doesn't have to look like formulas. No. Okay, you're getting away from just raw data.
You're bringing basic knowledge or structure into the.
And it's the same thing that have to do with causality. Causality requires that we have some models. Okay, if the whole world is there's an old cartoon. These two students are talking, and one student said, "Well, I've taken a statistic course, and I learned from the course that that correlation is not causation." And the other students say, "But this observation, is it correlated with the course, or is it caused by the course?"
Exactly. That's the critical problem that we have to face.
Yeah. So causality requires that we have some model of how the world operates. Okay. Very often it's hard. All that, if you just have data and you don't have models, you talk about correlation. You cannot talk about causation. Causation requires you have some kind of mechanistic models.
Right.
So I think there are different reasons to bring, in this Judea Perel says, if we don't have causation, we don't understand the world, and this machine cannot really become intelligent if you don't have common sense reasoning, you don't understand the world, and you cannot understand the world without understanding the concept of causality. Okay.
Yeah.
So this is the argument of Judea, which I think I buy and many people buy. And again, Shashua looks at it from just a less philosophical, more pragmatic view. How do we reduce fatality rate by a factor of 1,000? He says we have to use models to do that. We can't do it without models.
Yeah.
So I think the great integration that right now is required is to take the three paradigms of AI, the symbolic one, where I take broadly even formulas and models, the probabilistic one, and the neural one, let's call it. Okay.
Yeah. Right.
How do we integrate all of this? And right now there are many ideas. Okay. There are people who do tight coupling, put the logic inside of your model. Okay. There's some logic neural nets you can find that people try to put the logic inside. There are people who say, no, let's use loose coupling, which is to say, let's take, for example, different neural nets and have a supervisory layer above them that tries to decide, the judge chooses between them using more symbolic reasoning. So there are just different approaches. I think right now there is a whole noise and commotion, and it will take us a few years to find out. I think there is growing realization. I know IBM Research is putting huge effort into neuro-symbolic reasoning and a lot of interest in the topic. It's a bit subsided now because everybody now just talking non-stop about ChatGPT. But I don't think that this goal of trying to understand neural nets, be able to analyze neural nets, which sometimes again you use symbolic logic to analyze neural nets, but also integrating the different paradigms that we have instead of saying it's one or the other, to saying they all have their place. Right. They're all powerful paradigms. Let's see how we integrate them. To me, this is right now the kind of the holy grail of AI right now is to one holy grail. We can talk about other holy grail, but one is to just understand how we take different paradigms and integrate them.
Right. I mean, these are amazing topics. Actually, one of the questions I had for you, Moshe, was exactly what's the next holy grail, and this is definitely as you're talking about it, it makes sense that a lot of the traction and where young students or young researchers coming in could benefit spending more energy on these sort of interfaces of topics.
I mean, look, the other place that it kind of relates to that, but a bit more specific, and also something that I'm looking this day, is we're going to have more and more system around us where hard-coded controllers, the way we used to think, you write a controller, you just have to write code that specify exactly what it does. It will be trained controllers. Instead of writing, I can imagine some kind of e-bike where there will be some system to keep you balanced. Okay. And how it will, how do we balance on bicycle? I have no idea. I know that some years ago, I find myself there was a conference, an excursion to a park in the Netherlands, and my colleague and I missed the bus. And I said, this is a Dutch park. The bicycle. It's no problem. We have to just bike, we have to bike about 5 kilometers. It will take us just 20 minutes. And I'm not 20 minutes, but about half an hour we're there, even 20 minutes we're there.
Yeah.
And he says, well, there is a problem. What's the problem? I don't know how to ride a bike. And I said,
why is complication?
I said, it's very simple. All you have to do is sit on the bike and pedal. Let me show you in 5 minutes. I'll teach you, and then we bike. And then we spent 15 miserable minutes in which I tried to show him how to bike. Before I realized, it seems impossible to teach adults how to bike. If you know how to bike, you learn how to balance yourself on a bike as a child. Somehow the neural net of a child can learn how to bike. As an adult, I don't know if I won't say it's impossible, but definitely not. I remember when I learned to bike, pretty much somebody says, okay, here's the bike, get on the bike and pedal. Okay. In fact, they didn't even teach me how to brake. I started going and I realized oh my God, I don't know how to stop. And I jumped off the bike.
Right. So
So they didn't teach me how to brake. But as adults, something is very difficult. But now I can imagine we can train a controller how to balance a bike. Okay.
yeah,
So we're going to have system where some of the components are going to be deep neural nets, DNNs.
yeah. And this is
And how do we reason about the behavior of such system? We've developed
exactly.
lots of powerful, much of my own research over the years about trying to develop a technique to analyze
Mm.
the behavior of complex systems
Yeah,
using symbolic techniques.
right,
But this assumes that the system are given to us as hard coding. We understand the code,
right, right.
not consisting of some blobs of neural nets.
Mm. Yeah.
How do we reason about this kind of systems?
Exactly. And so this is, one of the questions that I want to get into is to think about. I mean, this is as a thought experiment here, Moshe. And I know that the impact of AI is a general topic that you are interested in. But let's linger a little bit more with support systems. And this is a thought experiment that I also gave Judea Pearl in the interview, where we can think about self-driving cars as support systems that hopefully, as we're discussing, brings us more safely on average than humans is driving. Uh, as an analogy, if we can think about self-driving governments or self-driving organizations that would support humans in their decision making at the collective level, that obviously has ethical problems and there's challenges along the way of what the core values are of that organization. But how far are we away from thinking about those types of support systems at the organizational level?
So I'm more and more coming to think that computer science made a strategic mistake early on. So when I was a graduate student, I remember there was a book published in 1980, and the book was called "What Can Be Automated."
Hmm.
And the whole book was this: what computer science does. It automates things, and it was a big survey of books. It was like a handbook about different things that can be automated.
Hmm.
The question the book did not ask is what should be automated.
Hmm.
Okay, what
Hmm.
should be automated.
That's a
Okay,
really very good point.
and I think that's a question all the way. You go back to Turing's. AI in some sense was born. Well, there are you can find precursors already in the 19th century.
Hmm.
Okay, all the way even to early people who basically Charles Saunders Peirce, who talked about the hypothesis about computing machines, and they says, well, if you can compute, we can mechanize reasoning. In fact, Leibniz was the first one to talk about mechanizing reasoning.
Yeah.
And there might be even something stories in Greek mythology about this idea. We can we mechanize even, can we imitate humans? Can
Hmm.
we build machine will be like humans? And but the question, if you go back even to the early days of AI in the late 50s, people didn't say, okay, what is the purpose of this? It
Yeah.
was more, we are technologists. We want to know what is possible.
Yeah.
Okay. What could be done?
Hmm.
Didn't ask what should be done.
Hmm.
So one of the slides that you saw in my talk about the siren song autonomous driving is
Yeah.
the difference between AI and IA.
Hmm.
So tools to help us. Yeah, we all would love tools to help us. We use it all the time. Okay. You now we are human. If you ask what's unique about humanity, if we still think we're just, we descended from apes.
Hmm.
And so we said, okay, we are more intelligent. Okay. But we are tool makers. We're not the only species that use tools. We find some other species use tools, but they don't make tools.
Yeah.
Okay. So a chimpanzee may use a rock to crack a nut to
Hmm.
get to the meaty part inside. Okay.
Yeah.
But we are tool makers.
Right.
Okay. This is the story of humanity
Hmm.
is exactly the story of tool making.
Hmm.
Okay. But this is what technology is about. It's about tool making.
That's a great
So
analogy.
And we use it all the time. How did I come to the office this morning? I drove a car. I used a tool. This was a tool to get me faster. Before that, we wrote animals, okay? But we have used tools to help us in many, many ways to make us more productive, so to speak.
Yeah.
And in fact, when you go to Leibniz, who thinks about these ideas of these hypothetical computers, call it a calculus ratiocinator, a reasoning calculus. What is the purpose? The purpose was to help us think. He said this will help us think the same way that glasses help us see. This instrument will help us think.
Right.
So people call this approach today IA, intelligence augmentation, as opposed to AI, which is I'm going to replace you by a machine.
I see.
And this question, you go back to Turing, who talks about 1950, the possibility of machine intelligence. And he asked, it's a philosophical paper. The paper is famous because of the Turing test, what we call imitation game. But I consider that to be the weakest part of the paper, because he's confusing intelligence with being able to carry out a human-like conversation, which is in fact only one facet of intelligence. Okay, there are many other facets of intelligence. Okay,
right.
Why not solve mathematical problems of certain types? Okay, all kind of problem I can think about. Solve ethical problems. Do ethical reasoning. I can think of all kind of questions about it. So the Turing test, as we learned, was flawed. And in fact, the first time, people think that ChatGPT can pass the Turing test, but it was already passed about a decade ago by a program that pretended to be a stupid Ukrainian boy who knows nothing about the world.
Oh yeah, I've heard of that story. Yeah.
So it turned out, instead of trying to in fact, the strategy was, why try to be intelligence? I will mimic being human by being stupid, because there are lots of stupid humans. So this is the way I'll pretend to be human, is by being stupid. Okay.
Yeah.
But the rest of the paper is really, I think, still, I go back and look at the paper, and he say, okay, what are the philosophical arguments against machine intelligence? And he decisively, he wanted to use the imitation test to define intelligence. Okay. And I think it was a poor definition. But let's suppose that we don't define intelligence, but we use, there was a famous quote by a Supreme Court justice about pornography in the United States. He said, I can't define pornography, but I know it when I see it.
Yeah.
So let's use the same definition right now of intelligence. We are not going to define it, but we know it when we see it.
Yeah.
So Turing asked the question, is there any philosophical barrier towards the concept of machine intelligence? And he answered all the objections fairly decisively. And he said, okay, so now let's get on the project. But there's no reflection there. What is the purpose of the project? Why should we build machine intelligence? What is the purpose? Okay.
It's almost like what, we go to the moon because we can, basically, type of attitude, right?
Yeah, but by going to the moon, well, actually, we didn't go to the moon because we could. We went, US went to the moon because we didn't want the Soviet Union to go first. That's
right.
That's the
true story. Okay. Exactly. That's
a true story. And there are debates about why should we go to Mars, for example. It's going to be a huge effort, very risky. Why should? And people are coming with. We can debate it, but people are trying to come up with some answer. Why should we go to Mars? Okay,
right.
It's not just because we can. Because it's in fact what John Kennedy said. We'll go to the moon not because it's hard. No, there are hard things that are smart try to do, and there are hard things that are stupid to do. And you should do them just because they are hard. Okay.
That's a fair point.
It was a rhetorical device, but it's not a good answer. We should do it because it's hard. Yeah. There were good answers. There were pragmatic answers why we did it. Okay, but you shouldn't try everything just because it's hard. But one thing you should ask is, what are the consequences? Let's suppose, what will be the societal consequence of going to the moon?
Yeah.
And the answer was, well, it will be, at this point, it will have a PR victory against Soviet Union. It would show that the West is ascendant, but nobody came up with a doomsday scenario about what will happen if we go to the moon. Okay.
That's why the vision also died out after the collapse of the Soviet Union. No one is really going to the moon now.
Yeah, because there was no reason to go to the moon. Okay. And in fact, now there's time to go again to the moon, and now we're going to the moon to learn how to be in space, or maybe so we can go to Mars. Okay. Which There's a whole other debate. Let's not go there right now.
Yeah.
But the question is, the people who start building AI they were technologists who were fascinated by the technology and are fascinated by the question, what could be automated? And for many years in computer science, this was the reigning dogma. What could be automated? If we could, let's do it.
Yeah, yeah. And so
And
what would you respond to this, Moshe? Sorry to interrupt you, but like, what would you respond to the computer scientists and the audience that might say, oh, but that's up for, philosophers or social scientists to debate. Yeah, our role is to really, again, explore the possibilities of technology.
so basically this is really the way, unfortunately, where many computer scientists think, okay, I'm just the nerd. I'm the nerd in the room. I'll develop the technology, and I'm going to let sociologists and philosopher and humanists think about societal implications.
Exactly, exactly.
And to me, it's just not morally acceptable anymore to say that. Okay, if you are unleashing technology that can cause tremendous damage, and and the talk that I gave in February at Gothenburg, and talk about the damage that technology done to democracy.
Right.
You can say, well, I was just the nerd in the room. Okay, other people should have the objected, because what happened is the business people were developing the technology. Now we know that the business people are trying to do. What are the business people trying to do? They're trying to make money.
Yeah.
And so who's listening between the technology and the between technology community and business community? Who's listening to philosophers?
Yeah. No.
I mean, I mean, I mean, I don't remember when Facebook was going to start that Mike Zuckerberg said, "Wait a minute, I first need to run a seminar and consult with the philosopher. I'm here in the Bay Area. Let's go to Stanford philosophy department
Yeah.
and ask them what will be the consequences
Mm.
of social media driven by advertising revenue,
Mm.
with the goal of maximize user engagement. Let's talk to philosophers and sociologists about it." Okay.
That basically never happens. Oh,
In
very
fact, in fact, they did go to psychology. They did go to social scientists.
mm.
But the question they ask them is not tell us what can go wrong. They tell us, how do we make this as addictive as possible? How
Right.
do we maximize user engagement? And the psychologists get them advice how to do it. Basically,
Yeah.
they use their knowledge. And so if we have people who not don't have what I call social responsibility,
Mm.
then the fact that at the end of the day, three philosophers will write an article in a journal of obscure philosophy, and they will publish an article about the danger of social media, it's going to have no impact,
Yeah. Yeah.
because between technology and business and even instead of the psychology thinking about what damage can this system do, they say, oh, we know psychology, we know how to make the system
Yeah.
more engaging. And
So
so the question is, it goes back to, do we have social responsibility?
yeah, yeah. And this is something that you've written a lot about and lately, and also not only yourself, this letter as well, with a 6-month ban or hold on AI development in general. And this is, there's a huge backlash in a way that you might say, how will this affect development of AI in this domain? And could it also go to that extreme that it might even hamper the good development, the good impact?
So I disagree with almost everything in the letter, but I signed it nevertheless. So why did I sign it? I signed it because I thought that the status quo, where the technology and business community decides where we are going, is not acceptable anymore. And here there was an opportunity to have many people coming mostly from the tech community and the tech, both the research, both academics and the business, that saying, wait a minute, this is dangerous. Okay. Do I agree with stopping for 6 months? I don't know how you stop something for 6 months. What is the button? Where you push the button?
Right.
And how do you stop it worldwide? It's not just enough, you have to negotiate. It will take 6 years to negotiate a 6 months pause on technology. Are we going to let China proceed?
Yeah.
And while we are pausing, so
Yeah.
it was completely unrealistic. Nevertheless, what I read, my summary of the letter was the tech community is saying publicly,
mm,
this technology is too important to leave it to us.
mm, mm.
We cannot be alone, be in control of this technology. If I had written the letter, I would have written it completely different letter.
Mm.
But nevertheless, here you have 1,000, let's call them generally, people from the leaders of the tech community
Yeah.
who are saying we cannot be trusted to manage this technology. This is what it says. We cannot be trusted. Society must have a say on where this is going.
That's an amazing statement if you think about it. It's really really saying that, you know, we know everything we know, the accumulated knowledge in that group of 1,000 is just like incomparable. But yet, you know, that you have people saying that.
We cannot be trusted, they're saying. Society must have a say.
Yeah.
I use in some of the talks, I borrow a phrase from BMW. So BMW slogan used to be the ultimate driving machine. So I've never driven a BMW. I've rode once in my life in a BMW. One of my students graduated, realized that suddenly he's making, way more money than he can ever imagine, and he leased a BMW.
Yeah.
And he came back to give me a ride in his BMW. Okay.
Okay.
And I enjoy the fact that you can have driver side and passenger side air conditioning. Okay.
Especially in California or Texas.
Yeah. But some people really enjoy, they said that it's very different experience than driving I'm driving a Mazda 3 car or Honda Civic, very different experience apparently. So this used to be the slogan. Now they're being threatened by autonomous vehicles. People say, I don't need to drive at all. I can just sit in the back seat and watch TV, play video games, read, what have you,
Yeah.
whatever. So the new slogan is, don't be driven by technology, drive it.
Mm.
And I said, wow, this is a beautiful metaphor for society. Right now we are driven by technology.
Yeah.
And the slogan for us should be, don't be driven by technology, drive it.
Yeah.
Do it. Technology should contribute to human flourishing.
Mm. Mm.
And it's now doubtful that it is doing this. Yes, of course, technology, if you ask me, give up technology, okay? I mean, we cannot go back, even 50 years ago, we cannot go back. Our life has changed. We are very dependent on technology.
Mm.
But look at climate. I mean, the biggest risk right now is the climate crisis, okay?
Yeah.
Every year, the UN, what is ICPC, whatever acronym they have, come up with a more alarmed and more alarming report. And so we've let technology again, because why? Because it was convenient. I call it tyranny of convenience.
Yeah.
We are just, once we discover tools, we realize, oh my goodness, we can make life easier for ourselves.
Right.
Okay. If you are, if all of our reconstruction of Homo Neanderthal was, they had big jaws, and they had big jaws because they used to chew a lot. And people say, what is the natural? There is a big debate about paleo diet and what did people really used to eat. And the real answer is paleo diet was cooked food, because cooked food enabled us to have these tiny jaws.
Yeah.
And in fact, many of us have dental problems because our jaw is small and we have too many teeth to fit in our, some of my teeth are crooked. And my dentist explained to me many years ago, you have too many teeth for your small jaw.
That's interesting. Never heard that actually. Okay.
Yeah. So there are many people have too many. Why we have crookedness and everything? Too many teeth in a small jaw. Okay. So we are addicted to the convenience. Convenience always beats everything else.
Right. I was going to ask. Sorry, Moshe, I interrupted you. So I was going to ask you a follow-up question, but I really want to go into the macro strategy part, which is really important for you, and in terms of explaining where things are going in terms of the development of these things. But actually, one follow-up, a small one, which is that this convenience itself, some argue, is actually making us dumber as a collective, because it's easier to do things. We're not using our brain to the full. What's your thoughts on that briefly?
So this argument is made. I don't quite know exactly about the science over this, because it has the two sides, which is on one hand, yes, we know that in the there was a huge transition. We went from oral oral period to the written period, once we invented writing. And even when writing was more difficult, that's the technology. People used to memorize a lot. Okay, people will have much better memory than we have today. And today, when I was in school, I had to memorize a poem, some, really tiny thing. People used to remember just way, way more. Okay.
Yeah.
On the other hand, we have access today to much information. Where I'm able to process huge amount of information and find correlations and causation and connect the dots, so to speak. So, on the other hand, there was in fact a book called The Shallows by Nick something. I forgot his last name now. How the internet makes us shallower, because it's just all the, it's called The Shallows. I think it's all there. It's chewed up. We don't have to think too much. It's already for us.
Everything's okay. Yeah.
Yeah. So there used to be something called the Flynn effect. And the Flynn effect was that for many, many decades, average median IQ was rising. They had to renormalize it every few years.
Right.
People were performing better on the standardized test. Okay. And there was a question, why is that happening? And the answer was more education, more access to information. So the kind of question the IQ test tests for, people have more exposure to it. So IQ was rising. Now, in the last, I think 2 decades, we have moved to the reverse Flynn effect. IQs are declining. And what is the cause of that? Is this because of exactly this observation that we become intellectually lazy?
Yeah, sort of technology makes us so convenient so that we don't even need to think.
Yeah. So it kind of reminds me of somebody posted a picture I saw some time ago about people getting into a gym using moving staircase.
Exactly. That's really a parody of where the current state.
Yeah.
So Moshe,
I don't know if it was real or fake. I don't know if it was real or fake, but it was beautiful.
So Moshe, one of the things that transitioning into the many things that you've done, I'm thinking about the topics that we're discussing and across the domain. And I'm thinking about these sort of managing now your time, energy, and creating space for deep work. And now I'm transitioning into the macro strategy part of the conversation. So how do you navigate in terms of your deciding in terms of where to say yes, where to say no, and working on certain topics?
So I have to say that technology clearly got in the way of doing deep work. I remember being a postdoc, and I would go in the evening to my apartment. I was single. I go to my apartment. I had no TV. What would I do? I would read, and I would think. Today, it's much harder to find uninterrupted time for thinking. Okay. One is my inbox is always overflowing. I have not found a way just to control my inbox. I mean, at the end of every year, I just declare email bankruptcy. I just copy the inbox to an archive and I start from scratch. And I know I will every year end up with thousands of emails in my inbox that I have not been able to process. Now I will just try to tell people, don't take it personally. Okay. It's a fairly random, which I mean, something captured my eyes. I deal with it. Something I said, I'll deal with it later, and I forgot to deal with it later. So I have to find a good system to do it. Okay. And but there is another kind of difference in academic career, that as you get more senior, there are more commitment, obligation, and expectations of, when you are a postdoc, what do you expect it to do? Just write good papers. These are the expectations, nothing else. There are no other expectations. Okay. As you get more senior, the expectations are rising. Inside the institution, you expect to do all kind of leadership things. In the profession, you expect to do more leadership things. Okay. So that means, at the end of the day, only 7 days a week, 24 hours a day, we're flesh and blood human beings. Okay. I find out that I can work about 12 hours a day, but that's pretty much where I max at 12 hours a day. I'd have liked to work more, but I'm weak. I need sustenance. I need to take care of my body. I need sleep. So I just have not been able to go more than about 12 hours a day. And
Right.
and then of course there are family obligations and all kind of things like that. So that takes it away from there. So even realistically, I don't have 12 hours a day because of my other family responsibilities. Okay.
Right.
So um, so now you try to have, again, I don't have exactly many rules. I get lots of invitation, for example, to write articles. But writing articles is a big commitment. You can just pull an article in half a day or a day, right? It takes about a week to write an article, let's say. So unless I think this will have strategic value, I will say no to writing articles.
I see.
Unless I can find a collaborator. So one strategy I've had for many years now is find talented people who have more free time than you and have an impact by mentoring them. So do it with PhD students and postdocs. So it has been many years since I wrote a technical paper by myself.
I see.
Because it's just very hard to find the time to put the effort and into doing the thinking, uninterrupted time. Okay. I mean, I wish I could go be a postdoc again. Okay. Where you have no obligation. You have the whole day to think and write. People just, then I tell people who start faculty, what do postdoc want to become faculty position? Tell them you have no idea. Now this is the best job you ever have in your life.
Right. I mean, there's some deep intellectual enjoyment of doing deep work and driving an article. And then, because I was going to say, but isn't, that in itself, becoming senior and engaged in many different committees, a way of influencing the discipline and so on. And that's work in itself, but it's perhaps not the type of deep work that we sign up to do as we started our career.
It's a different type of work. One is your ability, for example, if you're a parent, you realize that you deserve enormous amount of joy when your children are doing well. In fact, we have a word in Hebrew that comes actually from Yiddish, which specify the specific emotions of pleasure when your children are doing well. So it really is a version of pleasure, but you only use it in a context. It's a pleasure, it's a little bit like the word Schadenfreude in German, okay? Which is when you have a joy where one of your enemies is not doing well, okay? and we don't have this word in English. So in English we use Schadenfreude for this.
Yeah.
Because there's no word in English for this specific type of pleasure, okay? And so this is kind of, we're a little embarrassed about feeling Schadenfreude because we should never feel fortunate when somebody else has misfortune. We should never feel pleasure when somebody else has misfortune. But we do, we're human beings, so we do it sometimes. But we have a pleasure when you feel really well when your children are doing well. And I get the same, I kind of think of my students as my generalized children. And I get a lot of pleasure when they're doing well.
Yeah, that's beautiful.
And in effect, my postdoc mentor said to me, Jeff Ullman, who was my postdoc mentor, told me once a line that stuck in my mind. I don't remember what I asked him, but he said, I'm mostly proud of my mediocre students.
Really? Okay. What?
And I was stunned. I said, you had some amazing, he had students who became big star, big names. I said, aren't you proud of this and this and that? He said, yeah, they're doing great. I'm very proud of them. But they would have done equally well with me or without me.
Okay, I see. The influence is...
Okay? I don't really feel that I've contributed to their success. I said, my weekend students just gave me bellyache because I invested a lot of time at the end. They never finished their PhD. It didn't work. But he said, but mediocre students, I really felt that their my mentoring made a contribution and they end up getting a PhD at Stanford or Princeton before that. And they go on to successful careers. And I can say, I played a part of it.
Yeah, it's an element of of an influence, of a contribution, of changing a human being's life.
Yeah, yeah, yeah.
And,
And I have had some students where I rescue them from bad advising.
mhm,
They're working with other faculty members. They're not getting good advising.
mm,
They ask me if I would be willing to become their advisor.
mhm.
And I was very reluctant because I did not want to view as someone who's poaching students from junior colleagues.
Right. Intervening also in colleagues' mentorship
Yeah.
and yeah.
In particular with junior colleagues.
Mm.
In both cases, the students told me, it's either you or I'm leaving the program. They kind of put a gun to my head, so to speak.
Oh, I see. Okay. That's serious.
And I said, well, if you put it this way, then you're not leaving me a choice. I'll take you as a student.
Okay.
And both have done very well.
Mm, mm,
And this gives me tremendous, tremendous pleasure. Okay, I made a difference.
mm.
And, you've kind of wanted partly this conversation to go into kind of big lessons for life. What is the big
Yeah.
advice for life?
Right.
And maybe about a decade ago, one of my PhD students asked me, what is the meaning of life? And I said, oh, this question is a black hole because there are really no good answers there. So don't go there. Just keep doing what you're doing. You're doing well. Don't go into this question.
Yeah.
And today I think I have a better answer. Okay.
Let's hear it.
And the better answer is to, I'm not a religious person at all. But I think religions sometimes offer us useful fictions, I call it.
Mm,
And one of the fictions that it offers us is somehow that after when you die, you have to account for your life.
mm,
And I think it's useful fiction because it makes you think, okay, um, let's imagine that I'm at the pearly gates,
mm.
Jewish, Christian, whatever, okay?
Yeah.
I'm at the pearly gates of some religion,
Mm.
and somebody's asking me, okay, what have you done in your life? And imagine that my answer would be, I wrote 700 papers. Well, whoever is the interviewer, I
Yeah.
expect this entity to tell me, we don't care about this here,
Sure.
right? Somehow that shouldn't matter. So what would I say? I would say there are two students who would have dropped out of the PhD program, but I stepped in and they have done well.
Beautiful. Okay.
Okay, that to me is a good answer. So at the end of the day, this question, what is the good life, is one of the earliest philosophical questions by the Greek eudaimonia. It was called by the Greek philosopher. What is the good life?
Mm,
And they say is that at the end of the day, the good life is a life where you helped other people.
mm.
And one of the things that kind of happened to us in modern, especially in American society, it became a very a narcissistic society. And for example, we've got people quote this invisible hand.
Yeah. Market
And
forces.
no, but the greater lesson out of this, there was a movie in the 80s called Wall Street, where this character Gordon Gekko,
Mm,
and he gave us a speech. You can find it on YouTube, where he said, "Greed is good because the metaphor, the invisible hand, basically say everybody can be greedy and will benefit everyone."
mm.
And in fact, this idea precedes him and goes to a Dutch philosopher who basically says private vice leads to public good.
Yeah.
Now there are technical problems with this. It turns out that it's just, first of all, technically, it's just not true.
Mm,
Okay, the idea is that the free market, all the free market does, it leads to what they call Pareto at the best. Under all the technical assumptions, it leads to Pareto optimal equilibrium.
yeah.
But it doesn't say anything that the public good is being maximized. It is patently false. It's just been shown to be patently false. Okay. But the moral implication of this was that private vice leads to public good. So it's okay to be selfish. It's okay for me to be nerd and just focus on the technology and enjoy doing it and not to think about consequences. Somehow everything will magically work out. Invisible hand will ensure everything works out.
Yeah.
Except it doesn't. It doesn't.
Mm.
And so, I've been thinking about the education the students at Rice get. And my son was a Rice student. He was a student here before I came here. In fact, I followed him. People think that when I tell them he was a student here, they say, "Oh, because you're a faculty member there." I said, "No, it's the other way around. I'm a faculty.
Okay.
I'm a faculty member because he was a student here. I got to know about Rice because he was a student here, and then later on, I decided to apply for a job here. Okay, because I like what I saw. Okay, so I didn't do a study, but I ran it on a few students. And I think this reflects what happened, especially in elite American universities. And there is a subtle message, implicit message. Nobody says explicitly, but the implicit message is you're getting great education here. And this is true. Really, Rice students get fantastic education. Go and have a great career, and you benefit from the generosity of previous generation. So be generous to Rice in the future. Because we're a private university, we really live on philanthropy. Okay. Income from student tuition is a tiny part of our budget, like 20% of our budget. The lion's share of our budget come from income from an endowment, which we have built now for over 100 years. From philanthropy. So our business people say, "What's your business model?" Unfair business model is reaching out with your hand and say, "Gimme."
Yeah.
So the students will tell you, we kind of tell them, you benefited from previous generation, you must be generous to the future generations. But I say never, but we rarely talk to them about social responsibility. We don't tell them, first of all, by just having a 4-year bachelor degree, you're roughly in the top third of American society. Okay, about 1/3 of Americans get 4-year bachelor degree. But you are getting a bachelor degree from elite university. You're likely to end up in the top 10% of American society. So you have an obligation for the other 90% that are not so fortunate. And the thing that this free market ideology did, it just eviscerated. There's no concept of, students do not talk about social responsibility.
Right.
And they just want to go and become rich, have a great career.
Yeah. And so how do we bring this back, Moshe? I mean, this is what, in terms of leadership, if you think about leadership as a way of influencing your students and making them stronger, building them up. That's one way, but how should a mid-career or an early junior researcher think about this problem of giving back through, perhaps influencing or building, or how should we do that?
So I do it in a variety of ways, there's no magic knob that I can turn. Okay. I talk about the public good and the need for all of us to be cognizant of the public good. I give talks like I gave at Gothenburg about technology and democracy, trying to tell people, look, the technology can do good, but it also can do a lot of damage, and we're responsible for it. We have to take responsibility for it. I started at Rice about 5 years ago, a course on computing ethics and society. And first it was an elective. It became very, very popular with the student. And the students have been telling us this course must be mandatory. and the faculty, the CS faculty, just voted just a few weeks ago to make it a required course now.
Well done.
So every computer science student from Rice will get the course where we discuss the consequence of technology and how the thing that, you're going to, you can go to Silicon Valley, but there will be adverse consequences to society. And in fact, typically we say the people will be more adversely affected are the more vulnerable people in society. The rich people benefit usually, but vulnerable people suffer from adverse consequences. And so, we have to change culture. Changing culture is very, very hard. Takes a long time, and I sometimes, there is a beautiful story that I like. I just only recently read it, but I like it very much. It's called the starfish thrower. So this guy goes to take a walk on the beach, and you see ahead of him this young teenage girl walking, and she bends down, picks up something, throws it to the ocean. She keeps walking, bends, picks something up, throws it to the ocean. So he's very intrigued by this. So he speeds up, catches up with her, and says, "Excuse me, can I ask you what you're doing?" And she said, "The starfish were there was a storm last night, and the starfish were washed on the shore, and now the tide is going down. And if they stay here on the shore, they will not survive until the next tide. So I throw them into the ocean." And he said, "But there are miles and miles of beach and hundreds and thousands of starfish. What difference can you make?" And she bends down, picks another starfish, throw it to the ocean, and she says, "I made a difference for this starfish."
Beautiful. Yeah.
And the man listened to her and says, "Okay, I will walk with you." And they walk together, throwing starfish into the ocean.
Right.
So I don't have a magical knob to make a huge cultural change in society, to change the culture. Let's say I'll be happy with the change the culture in computing, but I'm trying to do one starfish at a time. And every time I have one of my PhD students says, "I don't want to go to industry. After what I've been hearing from you, I do not just want to go to Silicon Valley." So it's one starfish.
It's one starfish. Beautiful. I mean, this would be a way of building, a momentum towards a group of people throwing starfishes into the water.
That's what we need. That's what we need.
Well, Moshe, what would you say to those that are early in their career and they're saying, I have 20 papers, I have 50 papers, I just need one other paper, and that's perhaps more important for me than mentoring. What would you say to them?
So I will tell them the story about Kurt Vonnegut, the author, who invited to a party at the billionaire's house, and that the house is not a house; it's a mansion. It's just amazingly opulent. And the friend that managed to get him invited there says, "Look at this house. Look at amazing stuff. Something you and I will never have." And Vonnegut says, "Yes, but I have something that this billionaire will never have." And his friend says, "He's a billionaire. What do you have that he will never have?" And Vonnegut says, "I have enough." So I thought one of the questions you want to ask is about good career decisions that I made.
Exactly.
So I made several very good career decisions. So when I finished my PhD, I had postdoc offers between Stanford and MIT. And I was very, very, very torn. It's two fantastic places. How do I choose? I was paralyzed. I couldn't choose. You get two fantastic offers.
Yeah.
And I was telling a friend of mine, I'm torn. He said, "It's very simple. Stanford has better weather." And I said, he's right. There's no other way to break the tie. They have better weather. So Stanford, here I come. So I went to Stanford. And besides the huge influence that this has had on my career, just the connection that I made there and the research direction. Who knows? I don't know what will happen if I went to MIT, but I know I met my wife in Palo Alto. So that's one of the most significant things in my life. I met my wife there. So I just made a decision based on the weather. then about a decade plus later, it was 1981. In 1993, IBM business was not doing very well, and IBM research was suffering, and we had to do what's called de-staffing.
De-stuffing.
De-staffing. It's a corporate euphemism from letting people go.
Oh, I see.
And I was not enjoying myself at all. I said, I have to get out of here. But this was a recession, so it was not easy to get a job. And I ended up only with 2 offers. One from Rice. They wanted to hire me because I had management experience. They needed a department chair. And the other one from Bell Labs. Bell Labs at the time was the mecca of research. It was the most amazing research lab ever. And not only that, the offer from Bell Labs was financially better. And I slept on it for about 3 months. And then I decided to go to Rice. And people ask me, are you crazy? Small region, small school, you could go to Bell Labs. I said, no, my guts tell me I should go to Rice.
Interesting.
6 years later, there was a dot-com boom, then the dot-com crash, and then the telecom crash. And Bell Labs has never recovered from that.
Oh, wow.
And people tell me, how did you know? I said, of course I did not know.
Yeah.
But I had a premonition. After seeing what happened at IBM, I have a premonition. The industry is less stable than academia. Okay? So I made a decision to come to Rice. And so you make decision based on guts, on just feelings, internal feelings. And then about a decade ago, a large tech corporation wanted to hire me to start a new research lab in Israel. And that was I grew up in Israel. I feel very Israeli. That was tempting. And it was they never made you an offer. It was more of a conversation.
Yeah.
But I was curious to see what it would mean financially. And I remember telling myself, I bet I can double my salary. And then I started sniffing around. What would it really mean? And it turned out that I was very naive.
Okay.
I could have quadrupled my salary.
Oh, interesting.
And that's significant. At the end of the day, I said, you know what? Yes, I could quadruple my salary, but 1, I have enough. 2, I have something here that I'll never have in a tech corporation. I have my freedom of speech.
Yeah. Well, that's exactly.
And I'm not willing to give it up for money. So I would tell everybody, of course, you want to have a good career. You want to be successful. Okay. But there is a in the Jewish literature, there's a book written sometimes we don't know exactly, maybe 2nd or 3rd century AD. And it's called Saying of Our Fathers. And it's basically all about ethics. And it says, if you're not taking care of yourself, nobody else will. But if you're only taking care of yourself, what kind of a person are you?
Right.
And there's a lot of work to be done to make the world a better place. And you're not going to be able to finish it, but you must get started.
Right.
So this is the advice I would get to tell to young people.
Right. That's actually the word that I wanted to give you, Moshe, was actually the last word.
Yeah.
And if you want to end on this or maybe add to this, please feel free.
The last advice I would tell them, go to meetings on time, and I must leave now to go to my next meeting.
Fantastic. Moshe Vardi, it was a true pleasure having you on the show. we'll meet each other soon again.
I hope so. I hope so. It was a wonderful conversation. Thank you very much for giving me
Thank
this
you, Moshe.
opportunity.
Thank you, Moshe. It's all my pleasure. Thank you.
Take care. Bye-bye.
Bye-bye.